Hello everyone and welcome. Today we are excited to share our project Vocal Motion, a spatially aware, voice-controlled, 5-axis robotic arm powered by X-Core AI. Our technical director on the project is Andrew Kavanaugh, a global system solutions architect at XMOS and a URI graduate of 2008. Our project is comprised of 2 ELECOMP designers, myself, Mason Jacob, an electrical engineering student, and my teammate, Derek Raffretto, a computer engineering student. The sponsoring company on the project, XMOS, is a fabless semiconductor company headquartered in Bristol in the UK. Their mission is to change the way systems are deployed on silicon, and they do this through their unique lineup of advanced microprocessors, such as the X-Core AI. As you can see in the diagram on the left, XMOS technology is employed in a wide range of fields, including home automation, manufacturing and preventative maintenance, health and fitness, motor control, vehicle intelligence and security, and public safety. They are on the leading edge of IoT, which is the Internet of Things, and strive to deliver embedded computers for any application. The motivation for this project stems from the introduction of the 3rd generation of XMOS's X-Core AI. This more advanced generation touts DSP, or Digital Signal Processing, AI and I/O processing boosts that give it an edge over its competitors. It also features nanosecond timing accuracy, full-fledged SDKs, and a software framework that helps to minimize power consumption to under 55 milliwatts. Optimizations and a streamlined pipeline allow the X-Core AI to reach 1600 mega floating point operations at a rapid 800 megahertz clock frequency. Furthermore, the processor's software-defined flexibility means that it can be applied in numerous ways, as shown by the diagram on the left. The X-Core AI can be used as an advanced microcontroller, the brains for an AI-enabled device, a versatile FPGA, and a real-time processor to analyze and provide meaningful data, such as intrusion detection, in real time. XMOS is looking to back these claims and support marketability of their new chip through our project. As such, we were tasked with creating a hardware system utilizing an X-Core AI to serve as an ample demonstration of the chip's capabilities. The only requirements of the anticipated best outcome, or ABO, were that a PCB was created with an X-Core AI to control some physical aspect of a system using a motor or other means. As the team was passionate about robotics, we decided to take it a step further and strive to create a voice-controlled, spatially aware robotic arm. We defined our own requirements, namely being that we would use the BCN 3D Moveo, an open-source robotic arm, which has 5 degrees of freedom and is low cost because it's 3D printed, and this system would act on wake words and commands. Furthermore, we would create a custom modular PCB that would drive the 6 stepper motors required for the arm itself, and include the necessary hardware, such as microphones, to receive the audio input and hand it to the XMOS chip. The ABO for our project was achieved. On the hardware side, we successfully created a physical demonstration, the robotic arm, which you'll see very shortly. Furthermore, the PCB was designed and fabricated and was successfully used as a modular stepper motor driver. On the software side, kinematics, stepper motor driver software, and voice control software was all implemented successfully. I will now summarize the team's technical accomplishments in more detail. On the software side, we successfully created a development container, or an isolated environment, to facilitate development with the XMOS software development kit. We also implemented basic stepper motor control, forward and inverse kinematics, and parallel control and step generation. Furthermore, to control our TMC stepper driver, we ported the TMC stepper library from an existing Arduino implementation. Finally, using sensory voice hubs, model generation, and the examples in the software development kit provided by XMOS, we successfully created a voice recognition model and implemented it on the hardware. On the hardware side, we created stepper motor circuitry and control within X-Core AI. We researched components selection and sourcing for our 3D printed robotic arm. We 3D printed those components and assembled them. And then we also designed and fabricated our modular PCB. Our project will have a significant economic impact on XMOS. In terms of voice-controlled electronics, our modular PCB design will serve as a development board for future users of the X-Core chip to control multiple motors at once, and it can be used in designs for 3D printers and other multi-motor systems for voice-controlled electronics. We've also provided a software framework for any multi-motor system using an X-Core chip, which is a very valuable product. In terms of the company and industry, we have created a successful demonstration of the X-Core AI chip as requested, and not only that, shown that it is a chip that is both affordable and marketable. We've also demonstrated new capabilities of the chip by creating a unique 2-core system that communicates with each other and does parallel processing. A significant achievement using XMOS's silicon. The following block diagram shows a summary of our system. The main component is the PCB, which is comprised of 2 X-Core AI chips shown in purple that are X-linked together or connected together and can work in parallel. Furthermore, we have our drivetrain, which comprises of our 6 stepper motor drivers that can modularly fit into our board. We also have microphones that serve as inputs on our board and power supply circuitry to step down our 24 volts to the multiple power supply or voltages that we need, such as 5 volts, 3.3 volts, 1.8 volts, and 0.9 volts. On the right, you can see that this PCB then drives outputs, including stepper motors and our servo motor. This is what moves the arm. I will now summarize my individual technical accomplishments. I was responsible for multiple tasks, including the previously mentioned development container that was used with Docker and VS Code to create an isolated development environment for the XMOS software development kit. Furthermore, I used the Sensory Voice Hub online interface to create a custom speech recognition model and successfully deployed it to the development board for testing. My further technical accomplishments revolved around the hardware components of the system. For the robotic arm, I sourced and assembled all the components needed to create the BCN 3D Moveo, as seen in the image below. Furthermore, I spent most of the second semester designing and fabricating the PCB. In the image, you can see that there are 6 stepper motor drivers, which can be modularly lifted in and out of headers to allow users to select stepper motor drivers for the application. There are also the blue plugs on the top where the stepper motor can be plugged into. In the middle, you can see 2 identical X-Core chips, which are linked together and can communicate with each other and work in parallel. Scattered around the center of the board are also the numerous power supplies to step down the 24 volts, which comes in from the yellow plug on the left, into our other voltages, such as the 5 volts, 3.3, and 1.8 used by the system. On the bottom and left, you can also see all the I/O outputs that are available. On the header on the left, there is access to the voltages that are created. And furthermore, in the left, you can see that there are 2 level shifters, which level shift our 1.8 I/O up to 5 volt I/O and can be used for any purpose. The bottom row comprises of all the I/O taken from the second X-Core chip. There are also 2 USBs for debugging each chip independently, a LED indicator, and a switch button to reset the system. I will now introduce my partner and teammate, Derek Raffetto.
Thank you, Mason, for your excellent introduction. I hope my work is as impressive as yours. My main accomplishment was dealing with the software. My job in the software was to complete the inverse kinematics. You may ask yourself, what are inverse kinematics? Inverse kinematics are the process of getting the angular positions to create a XYZ or Cartesian position in space. If you look at the figure on the left, you will note a 2-joint, 2-length robotic arm. This is a very simple figure, significantly simpler than ours. However, it's very beneficial to explain. So what I want you to imagine, we have the red length. That red length is opened at an angle of Q1. Thus, we can represent its X contribution and Y contribution simply as cosine Q1 times the length for the X and sine times Q1 for the Y. For the green section, what I want you to imagine is that this green section is moved to the origin. And if I were to do this, you may hopefully notice that the green section's angle, X and Y, has been affected by Q1 and Q2, both together. Thus, as you can see, we would take the length of the second, the green, and multiply by cosine Q1 plus Q2 for the X, and times sine for the Q1 plus Q2 for the Y contribution. And on the right, you'll see a very simple figure for polar coordinates. My example on the left is in 2D. However, our example is three-dimensional. Thus, this same geometrical representation of the X, Y, Z contributions due to the angles would be transcribed into 3 dimensions using polar coordinates as our basis. After the kinematics were implemented, we actually needed to drive the stepper motors. We decided to use the TMC drivers, not only because of their support of stall guard and stall detection, as well as sensorless homing to home the arm. It also has extensive documentation and already performed research available online. In front of you, you can see a TMC library class hierarchy that was already created for Arduino. However, to use this library, we first had to port it for the XMOS microcontroller. To do this, not many alterations had to be made, mostly just the SPI implementation, as Arduino and XMOS do it ever so slightly differently. The next thing we wanted to do with these drivers was they supported all SPI mode, which would mean that you could send simply the position you would like the motor to be, and the driver would perform all the calculations to get you there. Unfortunately, we spent a tremendous amount of time trying to implement this mode and got it mostly working, but not consistently enough to be used for the final demo. As such, we unfortunately wasted a tremendous amount of time and had to abandon the all-SPI implementation. To circumvent this all-SPI implementation not fully functioning, we'll need to recreate the same idea using parallel computing, which is offered by the XMOS chip. On the bottom, you can see a figure that represents the SPI control and the step generation. You'll see tile 0 and tile 1 and threads. So tile 0 and tile 1 are basically 2 processes that run in parallel, and they can communicate to each other. And the way that the flow will work for our program is one of the processes, tile 0, is constantly checking for a stall, while tile 1 is sending out 5 different signals that move the 5 different steppers. And that will create the motion of a robotic arm combined with the kinematics to push it to specific positions in space. Here you can see a short 20-second video of the arm moving with 3 different joints. It's very cute. You can watch it spin and move around, and our final demo will be a little more impressive than this, but for a 20-second shot, we think this is enough to show you the arm moving. Last, we have our acknowledgments for the people who made this project possible. First and foremost, Andrew Kavanaugh. He was our technical director from XMOS. He has been incredibly helpful and knows everything there is to know about our project. This would not be possible without his help and knowledge. Brendan Smerbeck has also been incredibly helpful in the finance and debugging aspect of our project, as he is very knowledgeable on the subject of the microcontroller style that we have. And lastly, Dr. Sunak, who put all of this together, is maybe the most important of all, because our project would never come to light without his program. Thank you so much, everyone.